Sorry. Yeah.
Oh, there we go. Now I see there is the meeting being recorded. Okay, so I am going to talk about something that we've been working on for the last 20 or so years, which is namely trying to come up with empirical/analytical models of the PSF for comparison with our fiducial model of the telescope, as well as something users can use. So the X-ray observatory, the Chandra is an X-ray observatory. It has a really fantastic PSF, but it has a lot of structure in it, some of which we understand, some of which we don't. When an observer looks at an object, they want to know, if I'm looking at an object, am I seeing just a point source, let's say, or is there structure around the point source? If I have some astrophysics in my object and I want to test it out, what are the uncertainties in the PSF? So that, for instance, if I want to put a cloud around my object, what are the sensitivities to the parameters that I can actually measure with the telescope? And if I want to simulate an observation to see whether it's possible, how well can I actually simulate it? And so let's move on. So this is actually, for those statisticians in the cloud who want to ignore the next 25 minutes, this is the fundamental thing we're looking at. We take a bunch of source events, which you see in the black. We have a bunch of background events. We ignore all the two-dimensional structure. We turn it into a one-dimensional PDF with some sort of background subtraction. And then we actually integrate that to determine what we're calling enclosed count fractions or encircled energies. And we're going to measure the radius of fiducial fractions. And the key thing that we are having interesting difficulties with is, how do we determine the error on the measured radii? And so if you can hold on to that, we can move back into the world of astronomy. So a very brief description of how telescopes work, and I apologize if this is too fundamental. So when you have a faraway object, it emits light in all directions. As that light comes towards us, the light that's not pointed directly at us doesn't reach us. Eventually, by the time the light gets to us, all the photons are pretty much traveling parallel to each other, if it's as a point source. The parallel rays impact our observatory. Our observatory has 4 nested cylindrical shells. And they are reflected off of mirrors inside of the shells. They get focused and they hit a detector. So just for grins and giggles, we can see here, this is a slice through the telescope from the side, and we have X-rays coming in, they get bounced and they get detected. So each shell has a specific set of energy ranges that they reflect best at. So for instance, if you look down at this plot at the bottom, you'll see that the outer pair, the blue, has about, it puts in about 40% of the contribution at low energies, while if we go to higher energies, the inner pair, the smallest of the shells, contributes about 100%. And as the thing that this plot doesn't show is that the total amount of photons we can collect at lower energies is much higher than we can collect at higher energies. So if you're looking at a high energy object, you get many fewer photons and your statistics goes down. The other thing that happens is that each shell, when it generates an image or when it focuses the photons at the focal plane, has a slightly different shape to that pattern of photons at the focal plane on the detector. And now we're going to combine all of these 4 shells into one. Each of these 4 patterns is composed of different ranges of energy because each of the shells has different sensitivities. And when you put them all together, you get something. So I want to point out here that we're only really looking at the on-axis performance right now, because that's the simplest. When you go off axis, you get a lot of distortions, and so that's much more difficult. It's a two-dimensional, at least a two-dimensional problem, and it's actually many more, but anyway. So the key takeaway from all of this is that the PSF is composed of a whole bunch of different PSFs added together. But we get a little extra in here, because if you're familiar with most optical instruments or with the cameras on your phones, they take images, you get like a pixel that's full of photons. But in the X-ray land, X-rays, they're fairly rare, so we can actually detect individual events. And so that gives us something you can't do with other detectors. So each event comes in, we give it a time, we give it a position on the detector, and we give it an energy, and we take those positions and we combine them together to form an image. We still retain those event positions because that gives us more information. But first, before we get that image, we have to go through the telescope. The telescope moves, and it moves for good reasons. But when it moves, the source wanders across the detector. And it's not quite as messy as this, but there's this pattern that you need to take out all of that motion in order to create an image. And so there's something called the aspect system, which pays attention to where the telescope is pointed in the sky, and it subtracts that motion from the positions of the individual events to create an image in the focal plane. And so you're left with something which looks much less like this ball of string and something which looks more like an image. But one of the questions you might ask is that, so you get this blobby thing, but why doesn't your image look like a point source, let's say, if you're looking at one? And we've got a lot of things going on. We have mirrors which are imperfect. We have limitations on how well we can correct the motion of that telescope. We get pretty good at it, but there's still limitations, so there's an error there. We have systematic problems with the detector, and, well, they all add up. So when astronomers want to look at a source, say a point source, they want to just look at the intrinsic shape and flux coming out of that source. They can't do that. What they get is this thing. And so the question is, to an astronomer, is the thing I'm getting consistent with what I think it is, or is there some structure in the source maybe that the PSF, the telescope, is masking? How does an astronomer know when they get an image what they should be expecting? So that's where a model of the telescope comes in. We want to provide a model which gives the astronomer a good idea of, if they see a point source, this is what a point source looks like. So if they get something which doesn't look what they think of like a point source should look like, they have an idea of if there's something extra. So for instance, astronomers want to know whether they're getting point source or are they getting a point source plus an extended thing. The extended thing is exciting. Point source might just be boring. So one of the things that we have done in the past is we've built up a very detailed model of the telescope. I concentrate on the optics because that's what I've been doing, but we have detailed models of the detectors. We have ground calibration, meaning that we tested these things before launch. We've done, for the telescopes, we've based our models off of as-built drawings. We have finite element models of distortions. We have an awful lot of inputs. So one of the questions you might have is, how is it that we can't take all of these inputs and derive an error on the actual model that we provide? So if we present a picture or an image of a point source, what's the error on that image? How do we tell the observer that you can trust this to N%, or we have so much confidence that this particular structure is real? And the problem is, we have an optics model. Is it any good? That's a terribly good question. And the real problem is the definition of what good really is. So we've got their components, we have all the errors. but we can't combine them. And one of the problems is that some of the components that go into our models have errors that we don't understand. One of the things we have, for instance, is a finite element model of the stresses put on the mirrors by their support structures. And over time, those stresses can change because the mirrors are actually epoxied to the support structures. Now, back 30 years ago, they ran a couple of models, but the models disagreed with each other too, and the engineers told us, well, they're about 20% different. At that time, and we couldn't run sensitivity models to see how that actually affected the image. So we just knew that there were these intrinsic errors that we could not quantify. So some components in our models have no errors. The other problem is that when we confronted our models with observations, in particular for the mirrors, we tested them on the ground before we launched them. We discovered that there was a significant difference between the models when we measured the total throughput of the system, and that our models were wrong. So what we did is we took the measured throughput that we saw in the ground testing, and we sort of pasted that onto our model so that it was consistent. It turns out that it actually works pretty good well in flight, but that means all of the errors of the components that went into the model that would have affected the throughput, we can't use those. Because, for instance, we measure the reflectivity extremely precisely, or accurately rather, but we can't use those errors because we've had to put in the semi-empirical fudge. So on one side, you may say, well, your models all suck, they don't have errors. Why do you even bother with them? The flip side is that the telescope was so complicated that we were not able to calibrate every aspect of it. So we depend upon the models to tell us how the telescope was going to respond in areas we haven't calibrated. So even though we know there are errors in the models, we still need to use them, but we need to constrain the models as best we can with measurements. So I've spoken a lot about the optics. I can move on now. We have detectors as well, and we have two primary detectors. And one of them is essentially like the CCDs in your cameras, where you get these square pixels and you get photons in there and they generate events and we know where they are. But it has problems when it looks at bright sources, so we cannot use it to calibrate the PSF very well, because most of the sources you look at with Chandra that are point sources are fairly bright, and so we can't use those observations. And if we look at a lot of faint sources, that means we have to take an awful lot of calibration time. Instead, we've been using the HRC, which has a different way of detecting photons. It can observe brighter objects, but it has its own nonlinear degradation issues that we have to contend with. So one of the things with our detectors is that we've done a pretty good job of calibrating their spectral response. So we know how to map the energy of input events to the output up to the limitations of how well the detectors can actually see spectral changes. But we haven't done a great job of studying their spatial response, in part because what was done at ground calibration isn't immediately transferable to on-orbit, and because on-orbit our sources, the systematic problems with the detectors prevent us from doing really large targeted studies. And it always comes down to this big question, is when you see something in a final image that Chandra takes and you say, oh, there's something wrong there. You know, is it part of the detector or is it part of the optics? Which part of the model we're using to say what is truth, which part do we change? So there are sometimes we can disambiguate that, other times we can't. The other thing that is that as through the mission we've seen effects in the detectors that we've been able to correct for. And we use sort of, we do sort of filtering to remove events. We do a lot of things to clean up the data. And so they're phenomenological at times, so it's not always easy to understand if they're removing parts of the PSF. How are they distorting it? Are they distorting it? We can't model the detectors with all of those effects in them well enough. We don't have good enough models, so we can't, for instance, do a sensitivity analysis to see how those corrections have changed the PSF. Now, one of the things that we haven't really taken advantage of, I think, to its full extent, and it's a little more complicated, is that well, we have to model the aspect system on the telescope, and that is the part of the telescope, again, which corrects the positions of events for how, as the telescope moves around the sky. And so, again, it takes this thing that looks like a ball of string, it turns it into a nice, small, compact dot. But it also has another effect which we can use to our advantage if we can figure out how to do it. And this is sort of a little schematic of what a pixel in the ACIS sees during this motion through the sky. So this red arrow indicates essentially the track across the sky that the pixel sees over time. And whenever we record an event, we can't tell where in the pixel it landed, so we always give it the position of the center of the pixel on the sky. But we know that the pixel is moving because of the dither, and so we know that, for instance, here, this event 1, when it occurs, we know exactly where the center of the pixel was on the sky, so we can assign that event that position. So it turns out that you can actually get better resolution than 1 pixel for ACIS because of the dither. And that's something we haven't, I don't think we've worked with enough to figure out how to improve our knowledge of the PSF. It comes out naturally from the system. Sorry.
Quick question. So isn't that something that we already do? I mean, is this something that something else that you're talking about?
Well,
we can't bin at smaller than pixel size at this point.
Yeah, I'm talking about the models. We don't model how aspect works when we generate our images. We make the assumption that aspect is perfect and that it results in a, well, not perfect, but it results in a very small deviation from, it adds 0.03 sigma or whatever the number is to the position of the events.
Mm-hmm.
So we make the assumption, but I think that if we were to feed this into our simulations and we understood better how to do this, that we could do a better job. And it's a small effect. I don't know if that answers your question. In essence, right now, we just ignore aspect.
Yeah,
in our models.
Sorry, I'm still a little bit confused. So are we saying that it is the aspect errors that need to be modeled better, or is it that the aspect itself?
I think it's the aspect. The aspect errors are an average over a certain amount of time, and so I don't know for any particular observation that we know what the aspect error is for that observation.
Right.
And so when we're looking at an observation, and you get at the end, all of the events come together, and you don't understand what the relative error in the positions of all of those events are.
Mm-hmm.
So you may have a puffier PSF than you normally might have, but you don't know that because you haven't done an analysis of the aspect.
Okay.
And we don't do aspect in our models so that, for instance, we cannot take, we can ray trace with the aspect that's given to us and feed that through the system, but we don't do a sensitivity analysis to see how much that affects the PSF. You're right, this is a small effect.
But it could be a large effect, especially because nowadays because of the thermal limitations of the aspect camera. It's doing a continuous readjustment of where the telescope points. So there is jitter in the aspect. So it's not clear that it's...
It's another, it's one of the things we spend a lot of time looking at, for instance, the weirdness in the HRC and how it affects the PSF.
Oh, that too, yeah.
And so we spend a lot of time looking at, ACIS, but we don't really spend a lot of time looking at how aspect affects us.
Mm-hmm.
And so I was just thinking about, how, when I put this together, how aspect works and what we could do with it. So anyway, I will move on if that's okay. So the end result is we end up with a model of the Chandra PSF. This is a little rogues gallery of what we think the PSF should look like at different energies if you had a monoenergetic source. And you can see that as the source goes in higher energies, there is some sort of strange structure which pops up. And so the question you want to ask is this real? And we believe it is because we trust our models at that level. But we can't put a probability on that. And we can't say, if someone says, there's this bump in my image, is it due to that? Is that real? We can't provide any sort of a probability that this is real. We can say, yeah, we think it is, but we're not quite sure it's at the right level, anything like that. So there's a lot of ignorance there. So with all of that, if we go back to one of the questions, which is that if you want to test some part of astrophysics, what are the intrinsic errors in our knowledge of the PSF? So right now, the only way we can do that is we take our model, which is what we present our users, and we can compare it to observations. And we hope that we choose observations which don't have intrinsic astrophysical structure or weirdness, so that we can take a star and know it's a star and look at the resultant PSF and say, if we compare it to our models, we'll say, aha, that's the problem in the models. 2 dimensions is too hard, so we need to go down to 1 dimension. And so that's where this concept of a very simple statistic. So there are still a number of things that go into creating this statistic which lead to errors and uncertainties. So for instance, we have a source. It's an extended source maybe, or a point source. We have a bunch of events, and there's a set of background events behind it, which hopefully is uniform. It may not be. That's an astrophysical problem, trying to figure out what the quality of the background is and how we can properly isolate it from the source. So we need to figure out what the background is. Then when we want to convert anything into a one-dimensional thing, at least as far as primitive astronomy goes, you need to find the center of the source. If the source is not a nice round thing, what does center mean? Is it the center of flux? Is it the center of some sort of peak? Some sort of structure in the source? So, I mean, the PSF itself is not symmetric. So when we find the center, I usually use some sort of a weighted sigma, with clipping. So how do you find the center? The center does affect what happens. We often, when we find centers and we look at a profile, which you see on the right hand of the screen, we see that the center actually goes down because we've missed the center. And so we're starting to measure from the wrong size. Anyway, we generate a radial profile, we subtract background, we get essentially a 1D PDF. So what we really want to know is that one-dimensional profile consistent with the PSF, which means it's a real point source? Is it consistent in the core, but is it maybe broader on the out wing so that you have, say, a star with some extended dust around there? Or is it broader everywhere, which means it's not a point source with something around it, it's just a much bigger object. So this is what we want to quantify. And we want to quantify it so we can compare it between models and sources, and also to sources. I always tell the users, don't ever trust the models, trust what the observatory actually measures. So traditionally, this has been called the encircled energy function, but it doesn't actually measure energy. It actually measures how many counts you have inside of a region. And typically it's a circle, but it doesn't need to be. For instance, over the years, we've played with using ellipses. So there goes encircled. So I like to call it the enclosed count fraction. What it is essentially is an integration of the counts. It goes from 0 to 100%, or 0 to 1 if you're doing fractions. And you measure the radius at a particular energy or particular fraction and use that sort of as the fiducial measurement. You say, well, R50 contains half of the counts. R85 contains 85. If we go out to R95, there's not that many. We don't know the models well enough there. Is that a good place to stop to actually call it fiducial? You get to the problem is that you only have 5% of the counts outside of that. So there's a lot of uncertainty in where that R95 really is. So we try to stick with measurements that are, sort of in the outer 2/3 of the PSF. So, and we actually just recently have been able to finally, after umpteen years in orbit, construct an empirical PSF for the ACIS detector by co-adding a large number of very faint sources. And so we have this stacked set of sources. So each source has been centered and background subtracted and all of the other things. So we have, essentially, we've magnified all of our errors. We've multiplied all of our errors because we now have lots of sources with different backgrounds and different centering. So in any case, there are a few things that make using the ECF difficult. For instance, what does it mean that you're going out to 100% of your counts? There's a background in there. There's a background level. How do you know when background stops? How do you know when it starts? If you're in this is sort of an astrophysical question. If you're in a region where the background is actually not flat, how do you handle the fact that the background on one side of your source might be higher than the background on the other side of your source? So this is a thorny question. When you're dealing with a radial profile, it's a little cleaner, but not really. I've already said, how do you find the center of the source? But the real question is, what are the errors in the radii we determine? So it's easy to count. I can count up to, and I can count, and I can find I have 100 counts, so I know the radius where 50% of the counts is on one side or the other. But what is the error on that radius? So when you give a user a set of radii, and they want to lay it down on top of their source to see whether their source is consistent, you want to be able to tell them how well you think you know that radius. And that's the part that we've been having a problem getting to. And unfortunately, I had a lot of software problems, so my written talk stops on the next slide. So I wasn't able to push it any further. So this is the part where moving the count from one side to the other of that line, that partition, can change where the radius is. But I've tried bootstrap resampling, saying, okay, here's an observation. I will, take some out, replace the sampling, and see what happens. And what you end up with is the errors on the radii are minuscule. They don't make sense. They don't match what we think we know about the Poisson noise. And so the question that we have is, what mechanism or what formulation can one use to go about getting the error in that radius? And that's where I'm at. And Vinay, you can fill this in because you've thought a lot more about this particular thing than I have recently. So if you want to add something, please go ahead.
I'm actually a fan of the binomial. It's, at least compared to when we compare it against simulations, Monte Carlo realizations of PSFs, at least for Gaussians, it works pretty well. It is not perfect because we know that it breaks down for small radii as well as small counts and for large radii, but probably the best version that we have. It's better than most everything and everything else that I have personally tried.
Right. I know there are other approaches, and that's where I ran out of time to bring in my references on other approaches, and so I apologize for that. So let me see if I can find them. I know that one of the things with the binomial, though, is I don't know how it takes into account the errors in the measurements.
Essentially, the binomial should include the essential what we think of as the Poisson errors, because we are it's the same distribution really, right? I mean, you have n counts split into different different levels. The problem, of course, is that at least I haven't figured out how to include the background properly in it. Diab, are you there?
Yes, I'm there. I'm thinking.
Oh, okay.
I'm trying to find this other reference, and I realize it might be on my work computer that I don't have here. So let me see if I can find it. Was this the direction you thought my talk was going, Vinay?
Kind of. I was also expecting more details in terms of what you expect the HERMA model would be.
You mean in terms of the analytic form for it?
Yeah, or numerical, however it works.
Okay, I'm sorry, I misunderstood. So I apologize, but that's what I came up with.
Yeah, that's all right.
Is this really the quandary for students that you've advertised as?
The quandary is really the how to model the PSF, and with the different. Right. There's also this business of the empirical PSF that we've been working on, right?
All right.
And we, what are the difficulties in using that in real life? Because if your measured PSF is noisy, what would that do to a deconvolution problem?
Right. Well, the deconvolution requires that we have a model which doesn't have artifacts in it, right?
Yes.
And so we haven't got there yet, in the sense that I know one person has done heroic efforts to use deconvolution, but it's not a plug and play thing. Mm-hmm. So I don't know that we're close enough to, I don't know that we have enough we have a good enough measure of the 1D PSF to be able to do it, let alone a 2D.
Right. We have lost your screen share, by the way, if that's...
Yeah, because I was going to go and that was intentional so that I can go and find this reference.
Okay.
So I'm trying to find this reference, and there was another attempt which uses a form of binomial and something else, and I need to track that down. And I apologize again. I had problems with my computer.
So DF, this is Rafael here. I have a little question. So did I understand correctly that your analysis currently does not account for off-axis effects on the PSF?
Off-axis is much more. Yes, that's true. Well, we're focusing on-axis because when people look for structure in sources, they're usually looking for structure around point sources. Things that are larger, usually the PSF is, when you go off axis, you're generally looking at much more extended objects. And so the effect of the uncertainty in the PSF is smaller, although it's still there. So the answer, there's a long answer to your question of, we haven't done a real quantitative analysis off axis.
So it's not that you're looking at more extended objects as you go off axis, is that objects look more extended as you go off axis, right?
Yes, yes.
But did I get that correctly, that you said that the error is smaller in that case?
Well, I'm saying that typically when people look, okay, so the PSF broadens dramatically as you go off axis. It goes up quadratically, essentially, with off axis angle. So when people want to look at small scale features, they usually point the telescope directly at them so they're not affected by the broadened PSF. For larger objects, when you typically, the analysis you do off axis is looking at large scale structure, which is not which structure on scales which are larger than the PSF size.
Okay, I think I get what you mean.
Yeah, I can bring up a picture of what it looks off axis. It's much more complicated. So, and one of the things we do know is that our models do not get the relative. Our models are too bright in the center, or are they too dim in the center? We don't get the relative ratio of flux in the middle of the off-axis image and the edges correct. So.
Right, and I understand why that is important for people doing pointed observations of a particular target. But when people want to do exploratory analysis of Chandra data, there will be a lot of detections that are off axis, even if they were not the target of an observation. And therefore, it becomes important to also understand the off axis PSF. But I get your point that it's
yeah, I agree with that. I mean, if the key is that if you have a point source off axis that's isolated, and so you can then it's much easier to analyze, even if the PSF is broader and uglier. It's just that if you have a crowded field or you're looking at a diffuse object, because you have so many, you're essentially overlapping all of the point sources at all the different off-axis angles, so they create this composite, which is very difficult to disentangle. So if you have an isolated point source off-axis, I think it's a lot easier to do the analysis. Yeah.
Right. Thanks.
Dia, were you going to show the off-axis PSF?
Okay, I will do that. Hold on a second. The easiest thing for me to do is to show the our simulations, because that's what I have here.
I think you made a very good point about the centroid being not necessarily a good description of the PSF center.
Yeah. Okay. So let me grab the screen share again, and I'll just do my desktop, and see if I can find the actual. Here's our user's guide to the HERMA, and so. Let me see. We have a little rogues gallery. So this is a simulation which is actually pretty good. Let me make that bigger. Of a 16 arc minute off-axis source, and so you can most of these ripples will go away. This is pure optics here, but you can see that it's very asymmetric. It's got shadows from support struts. It has a number of sharp cusps in the middle, which you will see if it's large enough. And so somewhere around here are 5 arc minute off-axis images. And again, you can see that, and these are binned at a quarter arc second, 1/8 arc second. And so you can certainly see very asymmetric features. And we know our models don't have the relative brightness right. So one of the things that you also notice, if you go to a very bright on-axis source, here's a very bright on-axis source. This shows this is an ACIS observation of HER X1, and you do see the strut shadows, This is an artifact, this vertical line is an artifact of the detector, and this hole in the middle is also an artifact of the detector. It just can't handle high count rates. So those are, in somewhere we have, let me try not to make you dizzy here, but somewhere there's a picture of all of Little Rogue's gallery, and I can't find it. Where is it? Apparently isn't here. But there are a lot of images here that you can see all of the different off-axis. And if you go far enough off-axis, you can get these really strange scattering wings from the ghost rays coming off of a single mirror. These are these big loops. And we have seen these in ground calibration when we push the telescope to its limits. So we know those are real, but probably the actual relative brightnesses aren't.
So I guess your point, the point that you're trying to make, Diab, is that it is hopeless to try to model these two-dimensional structures, and we should actually just be looking at the 1D versions?
I think that we'll get the best bang from our bucks for the 1D in terms of what, I mean, users are pushing for, they're looking at, they want to see structure around small scale structure. This is where Chandra is being pushed, right? Mm-hmm. Everybody's looked at the large scale structure. Everybody wants, the resolution of the telescope is best on axis, and people are using that mm-hmm. to get their astrophysical stuff, their interesting stuff. So I think that's where our efforts should focus at first. I think unless we're doing, I've thought about doing some sort of machine learning technique to try to tweak the models using observations for off axis, but we have far too many parameters to play with to improve the models. So I don't know, you know, we have 8 mirrors, each of which has an offset and a rotation and a tilt. That could, you know, there's a lot of different parameters to play there. So on axis, I think, is the, gets us what probably 80% of the precision work with Chandra.
But I guess the question though is, if you do figure out how to model the one-dimensional, the radial profiles, how would you actually use that in a as deconvolve 2D images or model 2D images?
Well, I think the first thing is it allows a person to easily say whether or not something is extended. And then you can go in and do, I mean, when you're looking at, if you're doing surveys and you want to easily classify whether things are extended or not, having that knowledge allows you to do that much more, to discard objects that are not extended, so you can sure. look at the interesting ones. Mm-hmm. In terms of actually generating a PSF good enough to do a real deconvolution, I don't know how to do that right now. I don't know that the 1D PSF gives you any extra information. It may, you know, if we discover some bump in the PSF and we figure out how to fix that, that may fix the two-dimensional one. You know, I can't answer that question.
Okay. I guess we are actually in the Q&A time, right? If anyone else has questions, now is the time to ask.
I'm still going to try to find that reference.
Oh, wait, David, you have a hand up?
Yes, I'm being very polite today.
Why?
Jumping in like I usually do. I was just going to ask, and I don't, you know, if we can talk about summarizing uncertainty, you know, like we talk about Vinay, like if we want to take, you know, a PSF is uncertain and how we want to account for that in our statistical analysis, but they're massive, complicated, high-dimensional objects. Is there any way we can begin to think about summarizing what we do and don't know about them.
Maybe the 1D, the radial profile might be a better. We've been floundering because we have been trying to model the uncertainties in 2D, and maybe that's the wrong.
Yeah, it's definitely easier to think about 1D.
Simpler with 1D. Though again, that brings me back to my question of, suppose you do have, you characterize the uncertainties in 1D, how do you use it in 2D?
Well, I mean, and you don't believe it's radially symmetric. So yeah, that's complicated, right?
I don't know that you can. I think you just turn the whole world into 1D and work with that. I mean,
yeah.
Well, yeah, this is Aneta, but what if we have this, structures which are not symmetrical, like the jets, which have very small number of counts, and your uncertainty is average over, the azimuthal direction, then how do you deal with the uncertainties on the detected jet features, for example?
yeah.
So I think that's a different question, because you can start thinking about more asymmetrical structures close to the point source. But if you have even 2 point sources, in theory, these 2 point sources, if they are close together, will not generate the will not be well modeled by the spherical PSF and the errors in the spherical PSF. Maybe they do, but when I'm just thinking about this asymmetrical structures which may be detectable and interesting, and how do you quantify errors on those?
Yeah, and in fact, there is another argument against, we noticed recently that the HRC LETG zeroth order images have this asymmetry that kind of moves around. And if you are looking at if you're looking at just the radial profiles, you would not see any difference, but you only see the difference when you look at the 2D, because the asymmetry is still there, it's just in a different position angle.
Well, so what we were doing was bootstrapping, of course, but this doesn't account for the errors in the model itself. It just accounts for the statistical, or whatever, the ray trace error through the instrument, right? You don't include in the simulations of ACIS simulations the errors on that model. The model is fixed.
Right.
So when we simulate many PSFs, we only account for this ray trace error somehow, or uncertainty, statistical uncertainty. There is no model component, model error in that. And how to include that in this model, I think that's where maybe the place would be, because you have some idea of what are the at least errors on some of these parameters which go into the ACIS, right? And maybe, by generating different PSFs, using those uncertainties will tell us something about how this uncertainty impacts the final simulated image on these smaller scales. I mean, you must have done this, Diab, right?
I'm trying to wrap my head around what you just said. Could you repeat it, please?
Well, you have this, as you described in your presentation, you have, let me turn on my video. Maybe that's better.
Easier when you wave your hands.
So as you described in your presentation, you have a model for the mirror.
All right.
And this model was calibrated. So you have some parameters of that model, which is very complex and high dimensional, but you have parameters which have some uncertainties because you are fitting this calibration data.
Right.
So when you run SAO-SAC, those parameters are fixed, right?
Yes.
Yeah, so what I'm saying is that you can try looking at the impact of the uncertainties on these parameters for SAO-SAC by running the SAO-SAC within,
Right.
with those uncertainties included, and see how this impacts the simulated PSF, if it's even.
So that's, so essentially doing sensitivity studies.
Right.
The problem I see is that there are very, very, very many parameters, and some we can't really tweak, such as the deformation maps of the mirrors.
Yeah.
We no longer have the software that's capable of generating new versions of those.
Yeah, but Terry, but do you have the uncertainty on these parameters? Because yes, model is very complicated, but perhaps some parameters are not important in the final outcome of the PSF on the small scale, because some parameters will create a large scatter, right, and some parameters will not. And I don't know the PSF model well enough to say which parameters impact the shape and the scatter to the extent. What we interested is in the asymmetric structures outside central core. So if you look at the ECF 90% ECF, whatever ECF fraction of 90, right? So within that or outside that, you may be able to characterize. I don't know. You have thousands of parameters probably. Yeah, I don't know.
There are certainly, so we could split the parameters into the ones that are. I don't want to use the word deterministic, but they're positions of things, right? So we have the alignment of the optics, the orientation. Those are ones that I don't know how well they were measured, in part because essentially the mirrors were aligned to each other so that they essentially were co-aligned with a light beam. And so we have, Terry was the one who derived, I believe you were the one who derived the angles and such of the optics based on that, but whether we could actually go back and determine how much of an error we could get in those positions based on the measurements, that's the HATS tests, Terry. I have no idea how easy that is. The other thing is we know that we have a problem with our scattering, the mirror scattering due to surface roughness. And well, we've actually, over the years, have been thinking about shifting to a new model to deal with that because we just can't get the old model to work. And so there's a question of, is the physics in that model correct? Or are the measurements errors? We don't know how to differentiate between the physics of the model and the possible, there could be measurement errors, but so we measure the surface roughness and then we input it into a model of scattering so that we can say if a photon hits the surface at this angle, it has a probability of scattering to that direction. But that's a mix of, two different things. So I don't know how we would tweak it. We know the physical model isn't correct because nobody has a really good model of scattering. I think that the thing is, Annetta, is every time we try to think about this, we end up going in circles because we can't really figure out where to start tweaking.
So I have a suggestion. We have done this kind of thing before with atomic emissivity models. And also, with the same thing that we tried with the effective area calibration curves. So essentially make a superset of possible PSFs that you can, using all the variation, the maximum variation that you can imagine. And then we can compare it to the data and actually select the ones that are in some sense better than the others. So we can narrow down this range of possible PSFs simply by sampling through, comparing it to real data.
How do we do that comparison?
For this, I will pass it on to David Van Dyke, who.
I mean, we're still stuck at, you know, I'm still trying to find my references, which I will find later and pass them around on figuring out what the error on R50 and R85 are. One of the things, yeah, so that's.
I mean, no, I was being a little facetious in the sense that, you know, the mechanism is, I think, reasonably well understood. Essentially, what we would just do is compute the likelihood with and without the, for this entire sample, and just look at which ones have the better likelihood with the data, and find a way to select them. So this is the scheme that we tried with the effective area calibration. In the Xu et al. Paper, and which is currently implemented in PyBlocks, but not really. And then we recently did this thing with atomic data emissivities. So there is it's possible to do this. Let's put it that way.
Yeah. So, but you need to have this the parameters which you get into, you can vary, right? For this SAO-SAC, you have to have some parameters to understand the, the impact of those. Because yes, this PCA, the composition of the effective area, this was one of the approaches where, after you had few thousands or several thousand of the effective areas, one can look at the possible contributions from different eigenvectors, right, and sort of describe that.
Well, I mean, the effective area thing was done with the PCA, but we don't need to do that. We can just use a sample.
No. Yeah.
In fact, that is something that that's the same scheme that Jeremy is trying. And it seems to work pretty well.
Well, some things, like some of the misalignments, are hard to characterize on orbit. They were actually derived from ground observations for a very limited number of off-axis angles and directions at a very limited number of energies. And
but if they're hard to characterize on orbit, that means we don't need them. Hard to characterize means they have little effect, which means it doesn't really matter what numbers you put in.
Well, you have a lot of degrees of freedom to play with.
Yeah, there are degeneracies certainly when you tweak one, but there are also you need to move some of them in. For instance, there are certain optical parameters that you have to change in parallel, otherwise you end up with distortions in the image that we know are not there. So,
that's good. You have some idea of the impact of certain parameters. So maybe looking at like the global, right? Not varying all of them, but the ones that they can impact the PSF, right?
Yeah, I think one of the things that's been holding us up, other than the fact that this is a huge effort, is that we need to be able to provide statistics which give us both. See, when we tweak something in the mirror model, we don't just affect the on-axis stuff, right? We affect the off-axis imaging as well. And so it's relatively simple to come up with a statistic you can use for the on-axis performance, because you can just turn it into a one-dimensional thing and just go with that. When you get to the off-axis stuff, there's a lot of structure there, and we have never really come, maybe we haven't thought about it hard enough, a way of quantifying the difference so that we could say, yeah, this doesn't make a difference, or yes, it does make a difference. And maybe we don't need to use that difference as a information to tell us what next to change. If all we're doing is running a zillion models and we're just trying to narrow, and we don't care to use that information as a diagnostic, but we still need to find some statistic that tells us how different something is.
Yeah,
but,
sorry, Go
what
ahead.
you can do,
Maurice.
like at the beginning, right, is you can take an off-axis source, and if people are going to hit me over the head with that, but essentially like a chi-squared or likelihood that just says it's really good or it's really bad is enough. Like you don't, because the parameters are degenerate, I would think at the first step that you change them and try to find out if I change them by this much, what's the, I would expect. So based on similar things I've done for like new instruments which don't yet exist, right, where I don't have to fit existing models like Lynx or something, I change models, and there's often a fairly narrow range where, let's say I wiggle the mirrors or wiggle the gratings, and I see how much that would do to the predicted PSF. And there's often a fairly large range, a very long range where nothing happens, and then a very long range where it's catastrophic, and we're clearly not in that regime, and a very narrow range where it's something in between.
Well, it has to be done as a simultaneous model for a large number of off-axis angles.
Well, so
It's
no, because
if
it's really bad for one off-axis angle, it's not the right solution, right? So I was suggesting
it could be good for one off-axis angle and be bad for others. So that's
right. But if it doesn't work for one off-axis angle, then it's clearly not going to work in general.
Yeah.
So I'm trying to narrow down the number of parameters so that you don't have to run 10,000 to the power of 10,000 models.
Yeah.
I mean, it's easy to eliminate bad models, and then you're left with a ball of possibly useful models, and that kind of defines your uncertainty in the PSF.
If you have a parameter A that for a certain scenario can only be 5.01 plus minus 0.001, then you don't have to test that for all other possible models too. Then you can move to the next parameter, and you can kind of iteratively go. Some of them need to be very together, but in many cases you may not need that. And so you don't have to sample the entire parameter space, which with a few thousand parameters is just computationally infeasible.
I was also thinking about right now about different projects. So, EHT, the black hole of M87, they have a lot of simulations, many thousands of simulations, which they compare to the data, and only certain models are represented by the data which are currently done. So they done sort of a different type of analysis, but they have simulations. So they do have, big simulations to generate the image. And then given the image, they're looking at the features in the image, which is the data image, and compare. I think it's probably a Bayesian model fitting, or, some kind of complicated hierarchical model, but they come up with the set of final models which can be used, not used, but are still consistent with the data. So, something like that could be done for the Chandra SAO-SAC model.
It would still have to be done for a large number of sources.
Yeah.
Know the properties of the sources, including their energy, and that they're not piled up.
Yeah.
But the question is how much you can narrow it down, like how much of that you need to do. Because if you have 1,000 parameters, but you find out that 990 of them are, you just need to run one on-axis, one off-axis source, and 990 of them are fixed to 0.01%, because otherwise it's catastrophic, then it suddenly becomes tankable to do that for the remaining parameters. If you find out that all parameters are terribly intertwined, like everything is dependent on everything, then that's of course much harder. But the way I understood it is that you don't know that that's the case yet.
I'm certain that we can separate out some of the effects we're concerned with. So I'm sure we can do that.
And we have plenty of data. For example, we have decades of AR lags at various off-axis angles, so we can do some.
Start with one on axis and see what happens.
Let's
you have to do off axis. Okay, yeah. Actually,
because
you're right.
What you change, if you change something, it affects off axis. and
Yeah,
it affects off-axis in different off-axis angles. So
right.
Yeah.
you
So,
can't
so
just
my
look at
suggestion
on-axis
is
and tweak things.
make a PSF for every one of the AR-lag positions for
Right. Different
So,
parameters.
so I'm going to disagree with you, Vinay,
Okay.
because I don't know that we can do a sensitivity study against observations because we don't understand the detectors well enough to do that. What we can do is do a sensitivity study in the models and say, here's the model we give you. If we vary a lot of parameters, does it change dramatically? So, you know, what's the level of variation we expect in the output model? If we actually want to compare it, especially on axis, to observations, then we have to deal with the errors in the models in our knowledge of the detectors so that we don't bake that into the optics.
But that is the point, right? So you have if you have, let's say you make a 1,000 separate PSFs based on slight tweaks to all the substructure parameters. And then what you'll get is a cloud of parameters which are reasonable fits to all the points, not just the on-axis, but also the off-axis sources. Things that are bad can be thrown out. So it won't, I would say look at it from not as trying to find the best model, but as eliminating the bad models.
Oh, I agree with you on that, but then what do we do with that? The next step is to say, well, how do we compare this to what's happening on orbit? So we take an observation, and if it's an off-axis observation, I don't care what the detectors do because it's big. So we can use off-axis easier than we can use on-axis because it's in the on-axis ones where the small systematic errors in the detectors will be degenerate with an error in the optical model.
Sure.
And so that's where, but that's the regime where where most people care.
No, let that be. All that tells you is that there will be an uncertainty, an inflated uncertainty in whatever deconvolution that you derive. Whether maybe what you find to be a jet is consistent with an artifact in the PSF, but that's okay. It's good to know.
But we don't know.
It's not a jet.
It's not a jet.
Yeah.
But I guess what I'm getting at is that we don't have a similar sort of range of responses for, say, the HRCI's imaging performance. Right. So you're asking for an exercise to be done for the optics, which I agree is a good one. And I actually started one about 15 years ago and never finished it. I just saw I just says, huh. But we have to do the exact same sort of analysis for the detectors.
That's
sure.
why it's useful to start with the off-axis, right?
Yes, it's useful to start with the off-axis.
And so if you can, all the models you can throw out based on the fact that they don't fit off-axis, you already know you can throw out without worrying about the on-axis.
I guess, the thing that has always, been a problem is trying to figure out what's a good statistic. I mean, you said just use like a simple chi-square subtraction, I guess, or something.
The choice of statistic is not important, I think.
Well, I have to write code to do something today.
Well, sure, chi-square. Chi-square is fine. I mean, if you want, you can just use a Poisson sum like.
But I have two images, which are large images, which have different structure.
Okay.
How do I determine whether it's that structure change is important? Do I say, that's the issue, is I'm saying one structure, there's a range of where the structures change a bit and I don't care. I don't know what that range is, so those are the things. I don't know, if I move a cusp of something, one direction versus flattening it a little. Those are two very different sort of things that I want. Do I want to measure at that level? Do I need to measure differences in structure? Do I just need to measure differences in, you know, relative flux between one part of the image and the other? Those are things that have, you know, that's the thing that we've been struggling with, is how do I know when something's really different?
But isn't that, I mean, you don't know if it's really different, but any of those methods will tell you those things that are the worst difference. And so what you get is you get an upper, even if your measure isn't perfect, you get an upper bound on your error. You don't determine how, you might find variability, you might vary your parameter, and there might be differences in there that your statistic doesn't pick up. But almost whatever statistics you do, if there's a difference that your statistic picks up, it's not a good model. And so if your if your model doesn't pick up a difference, there could still be one, but you get a bound on what the error is.
Yeah, for example, I mean, if you have a metal poor thermal, optically thin thermal emission spectrum, it could also be fit with a power law. You don't know which is the right one, but if the data cannot tell you the difference between them, you don't know. I mean, it's just, it is
And
what
for
it
a
is.
PSF model, either is good, right? Because why would you need the PSF model? Why would you need to determine parameters that don't change any observable quantity?
Well,
That
but
is
the
true.
point is there's, well, okay, so that's the problem, is defining what the observable quantity that you care about is. So when you're dealing with structure, and if there's a change in structure, that is an observable quantity that some people might care about, because, you know, it's different than, you know, it's, if you change structure versus reducing flux in different areas, but you maintain structure. See, there's, I understand what you're saying, and I don't disagree with this approach at all. And I think that in the past, perhaps I've been, what is it? Perfect is the enemy of good enough, or something like that.
Exactly.
Maybe I've
I
kind
think
of
that's the
fallen.
argument we are making.
Pardon?
I think that's the argument that Moritz and I are both
Oh yeah,
making.
I agree.
Yeah.
But
Well, that's how we got to the model we have, is good enough. I mean, it was an immense effort trying to derive those misalignment parameters in the first place, and that was using ground data, which has its own artifacts to deal with.
well,
There's
but
very little, there's practically no on-orbit data that's far enough off axis to really serve as a good constraint on those parameters.
well, but I guess the idea here, Terry, is we don't actually need brain power. We just need compute power.
Yeah.
So we know we don't have.
You need a way of telling whether they're different.
Yeah.
Well,
Yeah, that's the
okay, this
statistics.
is the part that I,
Highly resolved, high count images, and those are hard to get.
no, we have AR-LAC. We have plenty of AR-LAC.
Where
Again,
you have practically no energy resolution, and this
It
stuff
doesn't
all
matter.
depends on energy.
well, I think the key point in that Moritz made is that we really don't want on-axis stuff, because we don't have we don't know the detectors well enough, or we haven't done, the sensitivity analysis hasn't been done for the detectors at the level we need for on-axis comparisons. So we have to move to off-axis, which is the scariest part for us, because off-axis means you're tweaking mirror positions. It's one thing to tweak a scattering table. It's another thing to tweak the orientation and rotation of a mirror. That, I think, is something that we are very reluctant to do, but that doesn't mean we can't do it in software, of course. So
Yeah, we have to deal then with correlations between different off-axis angles and the effects of different energies.
yes,
We
yes,
don't
all
actually
those
have
things have to be
information
done.
on the energy.
To be honest, Terry, my biggest concern is writing the software to do all this. So I think this is definitely a step we should be taking. So I will accept all of your well-stated opinions on that, and try to think about how we can do this and at least start along this path. I still would like to have a better grasp of, for on-axis, what statistics we use and how we figure out how to handle background errors and count rate errors, so we have robust statistics we can use. And that's something that I think I will find my references, which add something to the binomial. But there's not a uniform opinion that binomials are the way to do this.
Well, there isn't. It's not uniform in the sense that different people are trying different things, but they all seem to end. Up in something that is close to binomial. There are small deviations from binomial, so I think it's not too bad.
Well, the question is, why are they going away from binomial, and what are those deviations taken into account?
That's probably.
I mean, that's where I have very little understanding of what's going on there.
By the way, I put a reference in the chat. It's to the second PyBlocks paper, which is the third PyBlocks paper, which deals with the so-called full base correction to the calibration, the effective area uncertainty. And I think that could serve as the model for this process.
Okay, I will. I can't seem to get to the chat. Could you just send that to the Astrostats group, please?
I'll send it to CXC Optics.
Or CXC Optics, yeah. Don't bother the statisticians. They know all this stuff, right?
Some of them, anyway.
Yeah, if it makes you feel any better or worse, I've had thoughts about doing the same thing for the Max internal mirror model. Essentially, and if the pandemic hadn't happened, I would have done that in 2021. But of course, now I'm doing in 2021 everything I thought I would do in 2020. So it's clearly not a really near-term thing, but I think the Max internal mirror model kind of misses the same thing. It'd be good if I could better say how good it is and how much it deviates from SAO trace, or maybe prove what it is, since I mean anybody can run your code, but if the Max internal model did certain things better, that would also help, because it's much faster and comes with the same install. So
yes, no, I agree.
It doesn't have the same, doesn't necessarily need the same precision that you want to achieve, and it's a much simpler model. But I have the same questions on how do you compare things, and how do you find what's the best, and how do you find if parameters are so correlated and you vary them together, and all the same questions. I mean, the questions are the same, just for a simpler problem.
Yeah, I actually easily found, I started looking at this at very latest 2011, because that's when I published some code on this. I haven't done anything since then. Okay, so I have, I guess we discussed what we came to discuss?
I think so. This was a very useful meeting.
Yeah, and I think I have to actually go to another meeting. So.
I mean, I was perhaps a little too optimistic in thinking that the statisticians could jump in right now, but I think it's still in a astronomers need to clarify things stage, and then have the statisticians have a back at it.
I hope I haven't wasted the statisticians' time today.
No, I don't think so.
Well, for the statisticians, so a question for the other astronomers: is there like a term or an underlying theory or something I can look for comparing images, essentially, that answers some of those questions that Diab has, and maybe is a little more sophisticated than what I said, just do chi-squared between the two? Is there other approaches or?
Sorry, Moritz, I think we lost the key word when you said comparison of
You
what?
couldn't be the only one interested, Moritz.
I know.
2D comparisons of Poisson data.
Is there anything that improves on comparing the two and just getting a likelihood? Any other metric or?
C-stat at this point.
But that doesn't really give you it doesn't give you the spatial sort of
Yeah, it's only
I mean, it's bin by bin.
By pixel information.
Yeah, I mean, I've looked at
something that isn't just bin by bin.
Yeah. I've looked at some image. I've been over the years. I've looked at image recognition techniques. things to look at gradient, so, edge detection techniques. So you could try to highlight structure and so that you could see whether structure is changing. All of that stuff.
Especially you're talking about residuals analysis, right? I mean, this is
and there's a lot of work that's been done for, looking at people walking for surveillance or for detecting parts on manufacturing lines. But when you're dealing with, it hasn't really, I haven't been able to find that sweet spot where I can point out a research niche which falls into what this is. Because everything I've looked at has been using characteristics specific to that particular thing they're trying to measure, which don't map. So I've gone and looked at a lot of this stuff over the years, and I've never really found anything which said, here's a technique you can use. I was really hoping the edge detection would come through, but no.
Machine learning.
I've asked this question myself a few times of statisticians, and there are some things that people have talked about, especially if you've got a large number of data points in your sample, in your model set. You can do a kind of a nearest neighbor calculation, that you can take every point in your space and calculate its distance from every other point in the space, and do that for your the distance between all the ones in your data space compared to the ones in your model space. And there are some model methods out there that say how to compute the significance of the answer that you get after that.
So this is akin to what astronomers would call like a 2-point or a 3-point correlation function? Going into cosmology?
I think, yeah, something like that, yeah.
Yeah, that's not the machine learning. I was just thinking about Thomas Lee Automark. Thomas is having this algorithm where he groups the data points, and I'm just wondering if this could be used on two images and then figure out if there is a difference in the images, significant difference.
Right now it only works for very large number of counts.
Right, so it's not a Poisson approach, but
it's Poisson, but even then,
but with large number of counts, yeah.
But that would actually
PSF will be
That's not a problem with simulations.
Yeah.
Yeah, but when you have to start comparing it to data, though.
No, right, but right now it's about the simulations, right? You want to compare the simulated PSFs and look for the features which are largely different. And
maybe, so we can generate as many counts as we need.
Yeah.
So could you send me a link to that somehow?
It's not familiar. Not published yet.
Okay.
But we are hoping to at least send it in by the end of this year. So I'll send you a copy.
Well, but you have but drive all the
you have a code, right? You have a code which can, like, you or the student can just try to run it on 2 different PSF and see what.
The code currently is very computationally intensive. So it takes him. The student, like if he has a 64 times 64 image, it takes him hours or hundreds of hours to do something reasonable with that. But I don't know if he runs it on multiple CPUs, but I believe that he can speed up that code significantly. If that works, that would help.
Yeah.
But in its current state, like it may need about the same time to compare the 2 images that Diab needs to generate them, and that doesn't quite seem right.
Oh, I can generate them a lot faster than hundreds of hours.
Depends on how many photons you put in.
Oh yeah.
Well, it can be turned into an image, Moritz, right? Because the same way as the solar case that we tried.
Yeah, but if it's still going to take hours for a 64 by 64 bit sized image, that's still well, it's something to explore.
Yeah.
Anyway, I think we've lost all the statisticians. Only the astronomers are left.
Yes. I should also stop recording.
Yeah.
But it's an interesting problem.